Okay, afternoon guys. This is lesson 3 on properties of waves from unit 3. Do pay special attention to some of the problem solving steps because these are going to help you understand the relationships between the wavelengths of light, which we have been discussing, and other properties of light, like the frequency and the energy that light has. So we've talked about how to find the wavelength depending on where an electron goes in an atom. So for example, what wavelength of light is produced when an electron drops from 4 to 2? What color is the light? And again, we said step 1 is to find the circle where n equals 4 and the arrow that goes to n equals 2. And step 2 is record the number attached to that line, and that's the wavelength in nanometers. So if we go back to this Bohr model, if we find the one that goes from 4, here's 4. Actually, that's wrong with 4. 4. Is there anyone on 4? 4. Oh yeah, I was right the first time. But not one that goes from 4 to 2. There is one that goes from 4 to 1. And there's one that goes from 3 to 1. Let's see, 4. Wait, is this one go from 4? No. Yeah, this one goes from 4 to 2. So 4 to 2, and then that's here, right here at 486. So if we wanted to find what the wavelength was for one that goes from 4 to 2, we'd find it, and it's 486. So 486, now that doesn't tell us what color it is. So if we want to know what color it is again, and this is stuff we've done before, but just to remind you, 486, if we divide that by 10 to the 9th, because these are nanometers, and here, this is in meters, then we'll get 4.86 times 10 to the negative 7th, and that's right in here, 4.86, because 4.9 is greater than that, 4.2 is less than that, so that's going to be on the green side of a blue color. And you should have seen that today when we looked at the hydrogen light. You should have seen that light that looked kind of teal. That would be the line from 486. Okay, so again, to divide it from nanometers to meters, whoops, we have to take that 480. Oh, I just moved everything. Oh, let me undo that. Undo. Okay, there we go, that's better. Okay, so to convert it from nanometers to meters, that moved it again. I want to move this. There we go. Then we need to divide by 10 to the 9th. And to put that into your calculators, 486 divided by 1, not 10, because the EE means 10, divided by 1, EE9, equals, and that'll give you the 4.86 times 10 to the negative 7th. And as we said, finding where it belongs at the bottom of the page, and that's to tell us what color. And we see that it was between the line between blue and green and the line that's blue to violet, so that means that that's a blue light. Okay, now when we talk about wavelength, a wavelength is the length of a wave from one peak of energy to another peak of energy. So energy is traveling. Electromagnetic wave is kind of a wave that varies between being electricity and magnetism. And it's a kind of funky thing. It acts in a lot of funky ways. Sometimes it acts like little particles. Sometimes it acts like waves. Hopefully the person who presents on Einstein will talk a little bit about this, because Einstein was one of the people who figured this out. So a radio wave can have a long wavelength, but a frequency is how many waves pass per second. So it's got a long wavelength, so not too many waves pass per second. And it's actually an inverse relationship. The longer the wave, the less the frequency is. So radio wave, long wave, not very much frequency. Not too many of them pass in a second. But if we go down here, whoops, that'll work. Red light is 7 times 10 to the negative 7th meters for a wavelength. So it's considerably shorter, teeny tiny, 10 millionth of a wave of a meter. That means that 10 million of these wavelengths could fit in a meter stick. So much shorter wavelength, so the frequency is a good bit higher. A lot more of them pass in a second. An X-ray is even shorter, 10 to the negative 10th meters. So 10 billionths of a meter, 10 billion X-ray waves could fit on a meter stick. That's a lot. So as these go by, they go by very quickly because the wavelength is very slow. The thing is, the relationship of these, all of them travel at the same speed. All of them travel at the same speed. All light, from radio waves to X-rays, travels at the same speed. It's just the number of waves that pass in a second that varies. Because longer waves, less are going to pass in a second. If they're doing the same speed, then these teeny tiny waves, a whole bunch will pass in a second. 10 to the 18th, that's a billion times a billion, will pass in a second. So again, amplitude is not something we're going to worry about too much in chemistry. It will be if you end up taking physics. But wavelength, again, that's what gives us the color of light. The color of light is defined by its wavelength. So this gives you another example. You can see these two different waves traveling at the same speed. Now light travels much faster than what this is showing. This is showing something like a water wave, but light travels very fast, 10 to the 8th meters in a second, almost a billion. It's like what? Not a billion, 100 million meters in a second is how fast light waves travel. So imagine this traveling so fast that 100 million of these these waves are traveling at 100 million meters per second. And then the wavelength is different between these two. So this wavelength is longer, this wavelength is shorter. So the number of waves that pass in a second here, let's count for just a second. 1, 2, that was pretty slow. 2 waves and it took several seconds. So this one, 1, 2, 3, 4. So these waves are way faster than these waves, as far as not faster, but the number of waves that pass per second, the frequency of the waves. This one has way more pass per second. This one has way less pass per second. So that's frequency. Waves are traveling at the same speed. If you are a particle in this wave, you'd get where you were going the same time as you would in this wave. It's just that the frequency of these waves are much slower. How many pass in a second? So this is an inverse relationship. That means as one gets bigger, the other one gets smaller. As one goes up, the other goes down. The ratio is the speed of the wave. Now with light, this is a constant. If you're talking about other things like sound or like water, their waves have variable rates. They can have different speeds. But light always travels at the same speed. And the speed of light is constant c. C is what is given to you in your reference table. I haven't given you the formula reference table, but that'll be in your formula reference table. And it's 3 times 10 to the 8th meters per second. So 300 million meters in a second. So the formula we use is the speed of light equals wavelength times frequency. C stands for speed of light. Actually, we're going to use F for frequency just to keep things simple, because this other symbol kind of confuses people. So let's just use F. Arial. There we go. So speed of light equals wavelength, and we have to use this lambda for wavelength because everybody uses lambda for wavelength. So anytime you see lambda, that's going to stand for wavelength, and that's what this funky symbol is. It's Greek. Lambda, wavelength. So wavelength times frequency equals the speed of light, and it's inverse. If this one's bigger, this one's smaller, because this number's always the same. Always. Always the same. So a couple of problem-solving hints that I'd like to give you, and this is what I would do for any problem you have to solve. And I know it's several steps, but once you get used to it, you'll be very familiar with it. So the first thing you need to do is list what you're given in the problem. If the problem gives you a bunch of numbers, figure out what those numbers stand for. I think when we were making mistakes on the density problems, it's just because you were assuming what things were. So look at the units and figure out what it is. The units for this one is going to be meters per second as a speed. Hertz or per second is frequency, and the wavelength is a length. So every time you have a length, it's going to be some form of meters. Meters, nanometers, centimeters, but it's going to have meters in the end if it's a length. So list what you're given first. Do that before you do anything else. When you're looking at those numbers, list out what each number is. Second, write what you're trying to find. Write down what your unknown is. Third, write down the formula that has those letters in it, those variables. You can only solve for one unknown variable. If you have more than one unknown, you can't use that formula. You have to find a different one or find ways to substitute things. Now this step will save you a lot of headache with trying to mess with numbers and trying to do algebra. Rearrange the formula using algebra so your unknown is alone, all by itself on one side. Then you plug in the numbers for each of the variables and solve for your unknown. Another hint, I know a lot of you are not familiar with scientific notation, so if you want to double check your answers to make sure they're right, if you're using scientific notation, which is the only thing that makes these particular problems challenging, I think, is that they're scientific notation. Really big numbers and really small numbers. So if you're dividing numbers that have scientific notation, then subtract the bottom exponent from the top to get an approximate answer. It will let you know if you're in the ballpark. So if you had 5 times 10 to the 8th, if you have 5 times 10 to the 8th divided by 3 times 10 to the 14th, to kind of check your answer and make sure you put it in your calculator correctly, take 8 minus 14, that gives you -6. So when you do it in your calculator, your answer should be close to 10 to the -6. It might be 10 to the -7th, might be 10 to the -8th, but it should be close to that depending on what these numbers were, the 5 and the 3. If you're multiplying, add the exponents together to get your approximate answer. So if you've got these same numbers multiplied, 5 times 10 to the 8th times 3 times 10 to the 14th, check your answer by saying 8 plus 14 is 22. So whatever you get in your calculator for your answer should be close to 10 to the 22nd. I mean, it's really useful to know if what your calculator says is even close, because I see people all the time just put down random answers that aren't even in the ballpark. Okay, so let's look at a sample problem. Let's look at the wavelength we got earlier, 4.86 times 10 to the -7th, and find out what the frequency of the wave is. Okay, step 1, let's list what we know. We know the wavelength is 4.86 times 10 to the -7th meters. We always know the speed of light. Speed of light is a constant, so 3 times 10 to the 8th meters per second is the speed of light. So our unknown is the frequency. Frequency is hertz or cycles per second, and that's our unknown. So we've listed out what we know and what we don't know. Next, write our formula. Speed of light equals wavelength times frequency. Okay, we want frequency, so let's rearrange it and solve for frequency. Frequency, let's divide both sides by lambda to get frequency alone. So frequency equals speed of light divided by wavelength. Okay, now, once we have this unknown by itself, let's plug in our numbers. 3 times 10 to the 8th divided by 4.86 times 10 to the -7th. We do 8 minus -7, it should be close to 15. Okay, let's plug it into, so if we're plugging these into our calculator, plug this into your calculator, 4.86 EE button, -7, then hit, well, you're going to do this one first. Put this one in, 3EE8, divided by button, 4.86 EE -7, and then you should get the answer, 6.17 times 10 to the 14th, and the answer is hertz, or per second. The meters cancel out and you're left with per second. So definitely try this on your calculator and see if you can get that answer. And again, that is close to 10 to the 15th, 8 minus -7. Okay, a couple more. Energy also increases along with frequency. So the more frequency, the more energy. So really short wavelengths have high frequency, high energy. Really long wavelengths have low frequency and low energy. So energy and frequency are directly proportional. As one goes up, the other goes up. Energy is measured in a unit called a joule. Energy, as I said, is measured in a unit called a joule. Now the value for energy is really tiny compared to the value for frequency. The difference is something called Planck's constant. There's a fellow named Planck who came up with this relationship between energy and frequency. And Planck's constant is 6.626 times 10 to the 34th, negative 34th, joule seconds. And the letter that stands for Planck's constant is the letter H. So this is a really tiny number. So that means each wave has teeny tiny amounts of energy. It's lots of light together that makes lots of energy. And again, the way to plug this into your calculator, 6.626 EE button, negative 34. So the formula that we're going to use, sorry, bells keep ringing, is E equals HF. So H is Planck's constant and F is frequency. So let's look at an example. I already have the answer down. So let me take that back just a second. Let's go ahead and leave it. So if we have a wave and its frequency is 2 times 10 to the 14th hertz, how much energy does it have? So first, let's list our variables. 6.626 times 10 to the 34th, that's a constant. This H, it's always going to be the same number. F is 2 times 10 to the 14th hertz, so that's F. E is the one we don't know. So we've already got it arranged, so E is by itself on this side, and our two things we know are on this side. So let's just plug in numbers for this, plug in a number for that. 6.626 times 10 to the 34th, and again, that's 6.626 EE negative 34 times 2 EE 14. And that'll give you 1.3 times 10 to the 15th joules. 1.3, and then it'll have a little 15 up in the corner for 10 to the 15th. Okay, so that's all we're going to go over tonight. There are some problems in your book that might be useful if you want to practice. As I said, there's some problems in your book if you want to practice, but tomorrow when you come in, we're going to be working on the next assignment, which is all about practicing using these types of problems with electromagnetic waves. So that's for tomorrow, and I hope you have a very good night, and I hope you enjoyed class today.